Okay, welcome everybody to this live question and answer session, which is following up on our last module, which was on ocean and climate. So I'm delighted to welcome Professor Jim Orr from the Laboratory for Sciences of Climate and Environment in France, and Professor Ulf Riebesell. I'll ask them to introduce themselves in a minute. And of course, all of you. So I have here online people introducing themselves. There's Damien from France, there's Mircea, there's Shevli from Bangladesh, I think, and Damien asking questions already. So anybody else who's online, start punching in your questions and we'll read them to Jim and to Ulf. Ulf, you know already from a number of lectures, but let me ask both of you, Jim, maybe you can go first, to say a few words about yourself and introduce yourself.
Right. Jim Orr, I work in Paris at the Laboratory of Climate and Environmental Sciences, LSCE in French. I'm an oceanographer interested in how the ocean is changing over recent time, over the industrial period and also into the future. And to understand these changes, I typically use numerical models, and the types of models you probably heard about already in this course in terms of they're used to project changes in climate, but we also, in these models, these Earth system models, actually we include also the carbon cycle, ocean biogeochemistry, terrestrial biogeochemistry. So I use these kinds of models to understand changes in the ocean and in the full climate system.
Thanks. Ulf, would you like to pick up?
Yes, yeah. Well, hi, my name is Ulf Riebesell. I'm a biologist, biological oceanographer at the GMR Helmholtz Center for Ocean Research in Kiel. Unlike Jim, I don't do any modeling, but I love to go out to sea. I collect data both on research cruises, but also very much so on what we call mesocosm experiments, where we put big, huge test tubes into the ocean and we try to simulate the future ocean and see how the marine ecosystem responds to that. So I collect data both in the field and in the lab, and I try to interact with modelers like Jim to make more sense of the limited data sets that we have.
Excellent. Well, let's go straight to the viewers who are joining us online. Damien says, thank you for sharing your time with us. I really enjoyed this MOOC. Glad to hear that. Damien is curious about the latest news and discoveries about ocean and its state concerning climate change. And he asks more specifically also, how about the current health of plankton facing warming, acidification, and deoxygenation? So I guess you just want, you know, hot off the press from the experts, an update. Ulf, would you like to start?
Yeah, I guess excellent question. Damien has hit right the spot. I mean, there's these three global stressors: acidification, warming, deoxygenation. They all impact marine life. They all impact marine phytoplankton. And that's exactly kind of the focus of our research at the moment, trying to figure out what will future marine ecosystems look like under these drivers. We're all working on this. We have done lots of experimental work on this. What we can say at the moment is ecosystems will change, definitely, because the change is going on so fast that many groups will probably not be able to change rapidly enough to compete in their ecological niches. So we're likely to see a loss of biodiversity and a change of ecosystem structure and functioning, most likely. But that's kind of a very sketchy picture. To be precise about what changes are going to happen into the future, I think we're far from being able to answer that question.
Jim, what would you say the current status of the ocean and climate is?
Well, I would say that certainly the changes are continuing. They're not slowing down in terms of the physical changes, in terms of warming, acidification. As long as the CO2 continues to increase and it's not slowing down, then we'll continue to have ocean acidification. The projections haven't changed really since the last IPCC report because it's a long-term process. The model-based projections, we're looking at more subtle aspects of these changes now, not only long-term trends and changes over the next decades and century, but also in terms of the variability of the system, both seasonal variability and differences between winter and summer, and how those will change into the future. For instance, we expect that based on recent analyses, that we expect that the seasonality, the amplitude of the seasonal cycle, winter-summer difference will probably double relative to present day by the end of the century as CO2 continues to rise. So that's one of the things we're working on now, and particularly in my group, and trying to quantify that globally, how that will change. Other than that, I would say there are not major changes in updates to give in terms of projections from models. We're just working now on the next round and bringing simulations, new simulations with new models, trying to prepare them for the next round of analyses, which is ongoing, will take several years.
Well, leading up from that, there's a question from the forum that I bring in, which leads straight into that. Nikita asks, what is the greatest uncertainty in the models itself, and how does that translate into the uncertainty of projections? If you would have a top list of what your major worries were.
I guess it depends on what you're interested in. If you're interested in acidification in the surface ocean, the greatest uncertainty is not in the models, but actually in the CO2 in the atmosphere. So the greatest uncertainty is actually us in terms of what we will do, how much CO2 will we emit as humans over the next decades, over the next century. That's really the greatest uncertainty. I think you can say the same for temperature change. The greatest uncertainty, the differences between the scenario, high and low scenarios, for instance, for the emissions of CO2 and other greenhouse gases, are large. Those are much larger than, say, the differences between the models themselves. So, but if we really want to start looking down into the models, what is the great uncertainty? There are larger uncertainties if you go deeper into the ocean, for instance. We don't know as well how changes in temperature, how changes in ocean pH will affect, will be evolving as we do in the surface. Nonetheless, we know that they are changing, and the models have a fair amount of agreement, but there's greater uncertainty as you move down in the ocean. As to what processes, I guess it's a general question. So if we're interested in climate change in general, there are large uncertainty in terms of the clouds and cloud feedbacks on the climate system. That's considered one of the larger uncertainties. And there's a tremendous amount of work going on into that. There's a lot of uncertainty also about how much ice will melt in the glaciers and in Greenland, how quickly that will melt in Antarctica. It seems to be relative to the last IPCC report. There's probably estimates are worse in terms of the amount of melting that will be going on. So I think I'm just touching on a few of the uncertainties. There are, of course, many uncertainties, but there's also consistency between the models are very diverse, and there's a lot of consistency for certain many things. And again, the largest uncertainty is really humans. Let's see how much greenhouse gas we will emit and what we will do about it.
Okay, well, let's take another question, change tack a bit, I think maybe more in Ulf's line. Mircea asks, I have a question. What causes massive salt blooms? And why do these happen in a short time, but periodically? That's an easy question, isn't it, Ulf?
Yes, sure. It's an interesting one. Yeah. Well, they do occur. Interestingly, and to be quite honest, we don't know what causes them. So the answer to the question is no idea. But of course, I mean, there's certain areas where they repeatedly occur. The definition of a bloom is that it's a massive outburst. So there's all of a sudden many of the organisms that make a bloom in a very short period of time, but it also doesn't last very long. So they disappear very quickly. Generally, we know that these salt blooms, they occur in high latitudes quite frequently. In the Southern Ocean, in the Arctic Ocean, we find them. If they occur, they have a massive impact on the entire ecosystem, the pelagic ecosystem, because they're like vacuum cleaners. They can take up particles, food particles from very small to quite big, and basically clean the entire water column of any available food. So they also have a very strong impact on biogeochemistry because they generate quite a bit of export flux. So whenever they occur, it is a major event ecologically and biogeochemically. But coming back to the question, what really causes their blooming, we don't know.
Okay, so one of the many things that I think we don't know, in addition to a lot that perhaps we do know. Shevli, who's very intensively part of our MOOC, asks James, talking of bias, which function in CMIP6, which I admit I do not know which it is, do you use to obtain those biases? It's a very specific question, so maybe Jim for Shevli.
Well, I must admit I don't know what CMIP6 is, but so maybe
okay,
if you
so
could clarify the question, yeah, that would be great.
Okay, so Shevli could pick up on that question.
Talking about cloud feedback processes, or I'm not sure.
Okay, maybe he can put his comment in while we pick up another question. And this is a very common question that has been coming through, I think, our whole MOOC in the forum. Paris asks how to develop management options and policy advice based on science if science is so uncertain. Who would like to start on that?
Jim, do you want to go ahead?
Oh, yeah. Thanks, Ulf. Yeah, that's really a tough question, isn't it? I think the first thing you need to do is to have good communication between the policymakers and the scientists, and that's always been an issue. There have been some improvements along those lines, but I think the basic hypothesis, if you will, of this question is that science is so uncertain, and science is not always for everything so uncertain. Some things we know extremely well, and other things we know not as well, and some things we don't know much about. But I think in terms of the process of summarizing the science, which is done every 6-7 years or so through the IPCC, that process is very specific about what we know and what we don't know, which I think is helpful. It's difficult, however, because there's so much information out there, and the IPCC reports are voluminous. The policymakers, of course, cannot read everything, so they do have a synthesis. They have a summary for policymakers, which is, for the last report, was less than 30 pages, and so they can read these kinds of things. So the uncertainties are very well laid out in terms of what we are highly certain about, what seemed very likely, what seemed less likely, and so I think maybe we should do know many things, and I think we know enough to motivate us as humans in the world to do something about it. Certainly, we know extremely well that I keep coming back to acidification, which is my specialty, but we know extremely well the ocean pH is changing. It's tied to CO2 in the atmosphere. The uncertainty of the models is almost entirely negligible. In fact, one hardly even needs a model to project that global average change in pH. Surface temperature, on the other hand, is more uncertain, but all the models project changes, consistent changes, that surface will be warming. The models have undergone a very serious evaluation and process, and the models are improving all the time. So we know, and indeed, as I mentioned earlier, the largest uncertainty is not between the models, it's actually between the different scenarios. In other words, how much CO2 we will emit, how much, what we will do as humans.
Can I add to that?
Please.
Yes, it's a great question. I think that's what concerns many of us as well. But I think it's a real strength of science to be able to quantify the uncertainty in our statements. And Jim just alluded to that. So that's what IPCC does with every statement, and what we try to do in our recommendations and evaluations. We also try to say, okay, how certain are we about a certain statement? And that actually brings me to the point is, to what certainty do we need to know things? So even if we can't predict precisely how ocean biology will change in the next 100 years, we know there will be changes. We know we're taking a large amount of risk. And this is what we have to communicate, I think. And then, of course, society will have to decide, is this a risk we're willing to take? Or is this risk too high for us? And would we like to kind of try to avoid those problems? And in fact, if you look at our daily lives, I mean, we take decisions based on high uncertainty. We pay insurances, not knowing whether our house will burn or not, and still we pay for that insurance, because in the case that it happens, we don't want to take the whole risk ourselves. So why do we need full uncertainty when it comes to ocean change or climate change? Just what the information we have, I think, gives us enough reason to say that there is time to act.
Okay, great. We've got more people come in. Yvonne from Guatemala, Ajit from India, Kitty from Hungary, and Chevly has tried to specify his question, Jim. I'll just read it out without, perhaps it's relevant for this, or maybe we could put it away for the forum if it needs more detail. Chevly says, I meant the bias in CMIP6 solar forcing when it comes to the impact of the solar tachocline on the Earth's climate. Is that something?
Yeah, I'm sorry. I think you'll have to put that aside, because I can't really answer that. I'm not a specialist.
Right. Well, Kitty's in from Hungary, and she has a question which is really more for the ecosystem module, but she says, my questions are, how does plastic waste affect the quality of the oceans and fishes as well? What happens if someone eats a lot of these fish? Is it harmful for humans? I don't know, Kitty, that this is the right place, but Ulf, maybe you can pick that up?
Sure, I'm not an expert on plastics in the ocean. The big story here may be microplastics, because this is what may make it into the food web. The information that I have is that we have very little solid data on the concentrations of microplastic in the ocean. There is some indication that some toxic substances may concentrate on surfaces of microplastic, which may then increase kind of the transfer of these toxics within the food web. So they may kind of facilitate accumulating those toxics along higher trophic levels. Whether or not that has already in the natural environment. In experiments, this has been shown, yes, it can accumulate, and if you provide very high concentrations of these microplastics then, or even nanoplastics, then you do get an accumulation. In the natural environment, I'm not aware of any data showing this. So even though it has been a major topic, I'm not sure whether we have any reason to be concerned about eating natural fish today because they might be, I don't know, accumulating the plastics themselves or the toxics that adhere to them. I wouldn't be too concerned at the moment.
Okay. We have some more questions on these multi-stressors that Ulf talked about so much. Yvonne asks, due to changes in temperature and pH and acidification in the ocean, how is the distribution of sea fauna affected?
You want me to start, Jim?
Go, please, yeah.
Yeah. There's both direct effects on the fauna. So among the animals, there are many, for example, that build their shells and skeletons of calcium carbonate, and those certainly have a more difficult time to grow and reproduce and just compete in the ocean, because the cost of producing calcium carbonate shells and skeletons increases with ocean acidification. That's a very simple concept that has been shown in many experiments. There's less building material for calcification, for calcium carbonate production, so it gets more costly, and that kind of drives these organisms into a state where they may be less competitive. Some of them may not even be able to do the functions, to perform the same way they did under non-acidified conditions. So that is a direct effect. There's also the indirect effect of changing food webs, and this starts at the base of the food web with the phytoplankton. I quickly alluded to that early on, that phytoplankton are affected by these stressors, acidification, along with warming and more local stressors, eutrophication, deoxygenation, and so on. So that also could lead up to changes at higher trophic levels, the faunal distribution. What that will mean in total, and where this is going to lead in the future, is very hard to say. One nice example, I think, where we can kind of get a window into the future are these CO2 venting sites, areas where CO2 is coming out of the bottom of the ocean. It's volcanic CO2. In areas where this is pure CO2 and not mixed with other gases, we can say, okay, these areas kind of represent future conditions of an acidified ocean. And what we see there is that the biodiversity goes down greatly, particularly if it's in coral reefs. Only very few of the corals are able to survive under those conditions. That affects the entire ecosystem, which is connected to coral reefs. So the entire biodiversity in these hotspots of marine biodiversity breaks down, and we end up with a very species poor ecosystem after that. So that's kind of a bad picture into the future, but I think that's probably the most likely scenario that we're going to look into if acidification continues for a few more decades.
Okay, let me pick up your that comment. There's several more questions coming in, but I have one from the forum that fits in there. Arash says, I'm hearing often that climate change will have losers and winners, but we seldom hear winner stories. Can you tell some? So, Jim, who's going to actually be the winner?
Well, Ulf is the biologist and I'm not, but I can say some winners that you hear about in the press are whales off of in the Southern Ocean. Because of warming, they seem to be thriving right now. Because Ulf can probably say more about this than I can. I'm not a specialist on the winners and losers argument in which organisms are actually out there winning. You could say that I think there are some organisms that don't have calcium carbonate shells, for instance, and they actually have small organisms called diatoms that are actually made of silicon. And these organisms, some people think, will thrive relative to, at least they will outcompete the other organisms which have to spend more energy to survive in an acidified ocean, for instance. So those are a couple of examples, but Ulf can probably give many more.
It's again that there's direct effects and indirect. There's direct winners, those, for example, that benefit from higher CO2, mostly plants, because plants need CO2 for photosynthesis. So some of them are very inefficient in using the inorganic carbon, the CO2 in the ocean, and those clearly benefit from high CO2 concentrations, and that relates to cyanobacteria, to some dinoflagellates, to some species among the phytoplankton, and even some entire groups. So those will definitely be winners. There's also indirect winners. Those, and Jim just mentioned, if a calcifying organism cannot compete in its niche in a future ocean, that may open up a niche. So there may be a winner taking advantage of that new niche. And so there's going to be a bunch of winners who can actually kind of grow into these open niches. The problem here is, and that's the example I just gave on the venting sites, that evolutionary adaptation is slower, for most large organisms at least, slower than the environmental change that we're seeing at the moment. So if the organisms are not already kind of set up to fill that open niche, it will probably take them too much time to evolve into it. So if a system is not set up to deal with those future conditions, we're likely not to see all niches, all open niches to be filled. But there will be some winners, many losers, and altogether, I think the safe thing to say is that overall biodiversity in the ocean will decline because organisms will not be able to evolve fast enough to fill all those open niches.
Okay. There's a question from Damien. Maybe Jim, if you can pick up on this. He asks, what are the impacts of acidification on marine export production? Is that something that plugs into your models?
Sure, we have acidification in the models, and we have marine export production represented relatively crudely. And I say that because Ulf has done research on this topic, so he would be better suited to answer what might happen in the real world. In the models, typically the formulations are not sensitive to that. We put these simplified equations that we put in the models are not sensitive to CO2 in these models, and when they have been made sensitive in terms of the formation of this organic matter, it doesn't have much of an effect, certainly not in terms of the feedback of this on atmospheric CO2. But these are models now, so it's not the real world. It's a simplification, necessary simplification in a very complex model system that we have to do. A lot more research has to be done. I think we're not so certain how it will happen, and the observational data on what would happen is also it's not sure what exactly will happen. But Ulf, can you say something more about that?
Sure. Yeah. We've looked into this question. It's a very valid question, of course, if you look at what possible feedbacks there are to the climate system from changing ocean productivity. The one thing I think is quite certain is that acidification will not change overall productivity in the ocean. Productivity is not limited by CO2. It's determined by the amount of nutrients that we bring up. So acidification in itself will not change that. Stratification of the ocean through warming may have an effect on overall productivity, but certainly not acidification. If the question is specific to how does acidification change export production, then I would say there are some hints that it may affect, for example, what we call the ballast effect. There's a lot of the organic matter that sinks down, only sinks down because it is ballasted by some heavy material. And one of the heavy materials that makes it to sink is calcium carbonate. And as we already said, calcium carbonate production will be more costly in the future and probably less prominent among phytoplankton or among plankton organisms in general. So a decline in calcification in the planktonic systems could lead to less ballast, which could then lead to less export. And that's something we've actually seen in a mesocosm study recently, where a bloom of coccolithophores, one of the major calcifiers in the ocean, it could not occur because of acidification. And then it had major impacts on export production, both of calcium carbonate, but also on the organic matter, which just sticks to these calcium carbonate particles and then sinks much lower. It gets degraded faster in the surface ocean, less CO2 is sequestered in the deep ocean. So that could be possibly direct effects of acidification on export production.
So thanks for that. Bayana Sharat joins us. He says, my question is, what factors and kinds of simulation models are considered to identify ecosystems as susceptible, resilient, or resistant? I'm not sure if that's an easily answerable question.
That's a question for Ulf, I think.
That is
we're having a lot of difficult, tricky questions here, aren't we?
That is well thought out question and not easy to answer. What we think is a fair statement to this is we've just discussed this intensely with in a group with colleagues of mine. In systems where you have a lot of redundancy, and this means where the same function is done by many different players in the system. In those ecosystems, you can expect to have more resilience. If there's only one engineer, basically, we often call them keystone species. If there's one species which does the job, like corals in a coral reef, for example, and that species is endangered, then of course the entire system may completely change, and you would expect low resilience. So it's kind of this back and forth between redundancy and resilience. High redundancy makes a good resilient system. A system which depends on very few organisms that can do the job will be more susceptible to changes. But I'm not sure if that answers the question completely. Jim, do you want to add to that?
No, I think that's a fine response.
Well, I have a question that I think really is for Jim. Claren asks, the Paris Agreement mentions 1.5 degrees Celsius, but we will certainly cross that. What does this mean for climate? Is 1.5 or 2 a magic number? I think this is a prominent question that one reads in the press as well. What's so magical about 1.5 or 2? What will happen after that?
Well, you're right. It's a very good question. I think the 1.5 is, in my opinion, unrealizable, but it is something which is a motivation, provides a motivation for people. Even 2 degrees will be extremely difficult to obtain. And it's just that we can imagine that it's difficult to say what exactly will happen at 1.5 or 2 degrees, or even if we go to 4 degrees. We know that the impacts from all the assessments will be much worse if we go much higher. So there, in terms of the impacts on corals, even at the 1.5 or 2 degree level, where we're talking about a lower scenario, which in the lingo of the IPCC in the last assessment was called the RCP 2.6 scenario. This is where CO2 is leveled off and comes back down almost to the level we have today. Well, this will actually require us probably to take CO2 somehow out of the atmosphere. And So I think there are many impacts that will happen even at the lower level, even where we are today. Corals, for instance, not necessarily from acidification yet, but from bleaching. We're seeing major bleaching events and mortality events. Last year alone, the Great Barrier Reef suffered greatly, and these have been increasing in frequency, in intensity, and things are only getting warmer. So one might imagine that at 2 degrees, corals will be in severe trouble. At 4 degrees warming, it's a whole nother world. So I think, well, any major coral reef systems still be viable. That's at 4 degrees. It's highly. It seems to me, not as a biologist, is highly unlikely. So temperature is a major factor, and beyond. And we're not even talking about acidification. The 1-2 punch of it, warming and acidification, of course, is even more devastating. So there are major differences between a world that 2 times CO2 in the atmosphere and 4 times CO2 in the atmosphere, and we can talk about these in terms of warming thresholds. But I think at 2 times CO2, with doubling of CO2 in the atmosphere, which will go beyond the 2 degree threshold, maybe that's the best we can obtain. But it'll be a really a different world already. And at 4 times CO2, we really don't want to go there. And I haven't really answered the question very well, but these thresholds are put there so we can, I think, to some degree, have a discussion, and they're easy to understand in terms of setting a threshold. The actual impacts, there have been discussions and papers on the impacts at the different thresholds of 2 degrees and 4 degrees, and probably don't have time to go into much of that here, but I think I'll leave it at that, and Ulf probably might have something to add anyway.
Yeah, if I can add to that, I mean, from all we know is that if we go much beyond 2 degrees, the impacts will be dramatic, both on terrestrial systems and on marine systems. But by the way, that the 2 degree warming corresponds to kind of a 0.25 to 0.3 pH decline, which is, again, a threshold that we would also put forward for marine systems to not go beyond without expecting major changes to our ecosystems. So it matches the warming limit, matches quite well with the acidification limit that we would put forward. Going beyond that, I think we're taking major risks. That's for sure. We're not in a place to say exactly what the impacts will be in terms of what ecosystems will look like, what ecosystem services will be lost to what degree, but the impacts will be massive to the extent that in large parts of on our planet, people will not find the same resources any longer and are likely to move out there. I think the big question that we as scientists are presently concerned about is what is the difference between 2 and 1.5 degrees, because that has been put forward also in the Paris Agreement that 2 degrees is the maximum, but ideally we would like to stay at 1.5. What difference does that make in terms of the predictions we have for the future? And that is very difficult to point out. I think we need to do more work on this difference. But as Jim already pointed out, it's highly unlikely that we will achieve staying below 1.5 degree warming. And even the 2 degree goal is ambitious. We need to change our system, our energy system, our economy very quickly to achieve that.
Thank you. I think that's good. Very nice activity in the live session. Bayana with the question on the resilience says, thank you for the answer. It was very helpful. You're welcome. We have Misha from Kenya who says, what are the main factors why scientists haven't been able to convince some governments to sufficiently tackle climate change? Is it really because it is an inconvenient truth? Take the challenge, Jim.
Oh, that's really a key question, isn't it? I think, and the answer is not so clear. Why haven't scientists been able to convince policymakers that this is a serious problem? I think we have. I think we have convinced them that it's a serious problem. What are people really willing to make the investment, however, because it's a huge investment. It involves a transformation of our entire energy system, from fossil fuels to non-carbon emitting energy sources. And this takes a lot of time. And we knew in the 70s already quite well. The scientific community was already extending in the 1970s. It was extending warnings, beginning to extend warnings that something should be done about it. But it takes time to be convinced oneself, and there are skeptics, I think, in the world who've had a lot of weight for some reason or another. It's convenient to believe that for instance, scientists don't know what they're talking about. That hobbyists, for instance, would know more. But I think policymakers, they have maybe a short-term vision, and whereas this requires a long-term vision. We need someone with a vision who's maybe willing to put to risk not being reelected to make major changes. And I think it's difficult to say exactly what the problem is. I think the scientists have been certainly over the last 20 years very clear in terms about the findings. The communication level has not always been there, I think, and to some degree it's been developing and improving. But I think in general the science is well known. We know the facts. It's just a question of actually, are we willing to actually make the changes, which will be costly in the short term, but in the long term it will end up saving a lot of resources and money. And so I think Ulf maybe have something to say as well on this.
I fully agree with what you said. I think it's not a problem of our policymakers not knowing about the issue. I think scientists have done well in communicating the problems. I think most of our policymakers are well aware of it, certainly in Europe, certainly in North America, and in many parts of the world, in fact. And the Paris Agreement is a reflection of that. I mean, that was signed by almost all countries around the planet, and it's a legally binding document, even though if you don't do what you've promised, nothing will happen. But it's binding for the whole world. We have realized that we need to change. So the question is not why do people not listen, or why people not know about it. They do, but the question is, why do we not act? And this is a question that goes to all of us. I mean, as Jim was saying, we have the knowledge about global change for decades already. Have we acted upon it? The CO2 emission development doesn't say we have done anything. We haven't come to act to respond to it. And this doesn't just relate to our policymakers, it relates to all of us. If we as a society want to make that change, then our policymakers will also pick this up. The technology is there. The money is there. We could certainly achieve it, except the will is not there. And that's kind of a question to social sciences rather than to natural sciences. Why are we not willing to make the change, even though we know better?
Thank you. Yeah, I think that is a big question. And as I said, it's really come up quite a lot in the discussion of participants within the MOOC. So we've got a very nice question from Yvonne from Guatemala. She says, according to the planetary boundaries, ocean acidification is in the safe zone. If this is accurate, why coral bleaching is increasing?
Well, the bleaching is not due to acidification, it's due to warming. Because at temperatures beyond 30 degrees Celsius, the symbionts are kicked out by the corals, and without the symbionts, they can't survive for very long. So it's a warming effect. But I think we're at the border. It's true right now. I wouldn't say that acidification is at a level where we expect huge changes to our ecosystems. But that's going to change very quickly in the next couple of years or decades. And I think one of the best animations that I've ever seen to that extent is one that Jim put up, where he showed how the polar areas are in fact getting to the extent the pH is changing to the extent that they become corrosive for calcifying organisms. This shows that major changes are expected in the near future. So we're going out of this safe haven into very risky conditions in the near future.
Jim, would you like to add on that?
No, I think it was a great response by Ulf. I think so. Can you remind me of the actual question so I can?
Well, according to the planetary boundaries, acidification is still in the safe zone. And the question was about coral bleaching, which Ulf has said rightfully is more due to warming.
Yeah, I think so. The rate of change of ocean pH is something which we cannot alter right now. So maybe if it's in the safe zone or close to being in the safe zone today, in a decade or more, it won't be because it will take us decades to phase out the fossil fuels when we finally decide that as a world community that has to be done. We've decided that in Paris, and the actions are ongoing, but the actual effects and the actual activity of reducing those emissions hasn't really begun yet to a serious extent. So it's going to take decades in any case for to have an effect on the trajectory of pH change in the ocean. So we will be seeing these changes, such as Ulf mentioned, in high latitudes, and in fact we're already seeing some areas where the waters have become corrosive to calcium carbonate shells, for instance, and these organisms that are being affected, that expect to be affected. These sea butterflies, they are part of the important part of the food web in some areas, at least in the polar regions, and they are expected to be affected greatly. So I think it's not going. If it is in the safe zone, it's not going to stay there. It's my basic message.
Okay. More nice comments. I have a question from San Yan. What is the role of long-term monitoring for following climate change? Funding organizations don't like to fund this. I think that's a very relevant question for scientists nowadays. Jim?
Well, it's exactly right. I think the monitoring is essential for us as a community. It doesn't sound maybe so exciting because one may have a difficult time getting a high-profile science paper out of a monitoring site, although it certainly can be done, but it requires years of investment, decades of measurements, the same routine measurements, which can seem boring to funding agencies, but are so important for us in the modeling community to evaluate the models, but not only that, to improve the future projections, we need observations. So we need to understand variability, which these long-term monitoring time series stations, for instance, provide to us. And the monitoring is not just about making a measurement in one place over many decades, but also about extending the measurement network out with novel platforms for measuring in the ocean. For instance, we have a new buoy system, Argo buoy system, which maybe you've learned about in this MOOC, but are being equipped also not only with the present system that has about 300 Argo floats in the water going up and down every week or so, making measurements of temperature, salinity, but they've also are starting to be equipped with other sensors to understand how acidification may change, so pH sensors, how oxygen may change in the water, and other biogeochemical sensors. So these kinds of monitoring systems are vital, and they're actually changing it's a new frontier we have now with all these new measurements, which not only do we have more measurements, but more measurements in some seasons in the high latitudes, which we were not able to get to with boats, with ships. We're able to access throughout the year now with these new monitoring systems. So monitoring is really essential, not only to understand the observation, how the world is changing right now, but also to improve projections in the future. Because with those, we've shown with models that we can actually reduce the uncertainty 100 years from now if we have the data. Now, not only by evaluating the models and improving them, but also by eliminating the bias with a model that's present today, because the models has had to be integrated over the whole industrial era. We can eliminate that earlier bias, and that improves our estimates for the future, in, say, 2100.
Ulf, do you have any examples of monitoring that have produced results that could not have been got in another way?
Yeah, I mean, I agree with Jim's comment. These long-term observationary data sets are extremely important for us to really look at long-term changes. And we have so few of them. The few open ocean ones that we have gone on for a number of decades are the one of Hawaii, the HOTS, the one of Bermuda, the bats, and the one of the Canary Islands, those three long-term data sets are highly valuable to our analyses of what changes are occurring. They have brought up lots of publications, but I agree with the question. It's been difficult to fund them and to continue funding them into the future. It's always been a struggle to get funding agencies to put money into this. And you wonder why is it so difficult for them to see the value of this and to provide the funding for that. So I fully agree. We need those long-term stations, observing stations. We need to convince the funding agencies to put in that long-term commitment, and they will continue to be of high value in our analysis of ocean change. Okay.
Wonderful. We have just time for perhaps one or two more questions. There's one question which I think all of you asked for with your lecture, which is really, if I can synthesize this was George in the forum. He says, how will we ever understand, knowing about single species, single environmental stresses, and short-term perturbations, how will we ever understand more complex systems? Will that need thousands of researchers for many decades? So I think his challenge is, how are you going to unravel the Gordian knot?
Yes, and the answer is we will not understand every single ecosystem with all the organisms in there around our globe. And that cannot be our goal, because it will take, as the question implies, it will take thousands of researchers for decades. What we need to understand is basic principles, and those apply to many groups, to certain functions in the ocean, to certain ecosystem services that we are very interested in. So if we understand these principles and we can show that they are actually of general nature, then we can try to extrapolate them to other systems that we have not studied. So the goal here is not really to understand or to study every single organism, but to see what are the major drivers, what are the major functions in the ocean that might change, and what ecosystem services are affected by this. And I think that's what we're trying. We're not trying to pin down every individual organism, but to look at big functions of the ocean.
Excellent. Well, maybe I think we just, with 2 minutes to go, I'd like to pick up a little bit and go into a sort of a finishing round. I'd like to pick out on what Eugen said right at the beginning, that our greatest uncertainty are humans. how our actions and our societies will develop. And people who've been watching the MOOC will know this is the original artwork that went into the graphic animations, and here we are. Humans are part of the solution. So I'd really like to ask each of you by turn to give us your reasons for optimism for the future. Who'd like to go first?
Wolf, would you?
Well, yes, I'm quite optimistic, and I think the reason is that we as a human race have shown that we are able to learn, able to adapt, and that we act reasonably, even though there's times when you're not sure that we're making much progress. I think all in all we're kind of up to challenge here. We have to get our societies to transform into a new state. But we're aware of this. We're on the way. Since the Paris Agreement, I'm quite optimistic that we have come to the sense that we have to act as a global population. There's no individual states that can make the change. It's we as a global population. And I think that realization has come through. We have the knowledge, we have the technology to do the change. It's just a question of whether we're willing to do it. And I think we're kind of on the step to going there, to actually wanting what we can do. So I'm optimistic that this will happen in the next 2 decades. If it won't happen, then we're up to huge problems. And I think we've come to realize this, and nobody can want this. So it has to happen. I'm just optimistic that we're a smart enough race on this planet to do that change.
Jim?
I couldn't agree more with Ulf. I think I'm optimistic because the alternative is so dismal that we're just not acceptable. And I think anyone with children, anyone looking into the future for humanity has to be optimistic that we do something about this, because it's just simply unacceptable otherwise. Now, there of course will be major impacts, but we can't let that set us back from the line, because if we don't do anything, the scenario is so terrible that we can't imagine the world that it would be. And I think it is enough impetus, I think, for almost everyone to be optimistic enough to invest in making a change for the future.
Okay, I think those are wonderful closing words, and I hope all of us can be part of the solution. Well, thank you to all of you wonderful people who've been online asking your questions and discussing, been taking the MOOC. Big thanks to Jim and to Ulf as well. Thank you very much.
Thank you.
Thank you.
And goodbye.
Bye-bye.
Bye-bye.